Welcome to the Explainer. If you've ever tried to string together a few AI agents and watch them instantly spiral into a chaotic loop of errors, well, you know exactly how fragile this technology can be. Today, we're diving into a fundamental structural transition happening right now in software engineering. We're going to unpack exactly how the Google.antigravity Python SDK is completely changing the game for orchestrating autonomous system-level agents, basically turning them from fragile toys into ultra-reliable engines. I want you to picture this contrast. On one hand, you have a developer painstakingly typing manual commands in a terminal UI, meticulously going line by line. We've all been there, and let's be honest, it is slow. Now contrast that with the modern reality, a Python script silently executing in the background. That's the Google Antigravity SDK autonomously spawning, configuring, and supervising multiple parallel agents at once. It's this massive, fundamental shift from passive text generation to autonomous goal execution. So, our roadmap for today covers 4 key areas: the engineering paradigm shift, programmatic agent orchestration, structured data extraction, and secure sandboxed execution. Let's kick things off with Section 1, the engineering paradigm shift. This quote really hits the nail on the head for our mindset today. Value migrates from typing syntax to defining intent. What this actually means is that you are no longer just a human code generator, right? You are a systems architect. Because AI models, for all their incredible power, they just can't guess your implicit business rules. They don't know your architectural preferences or your unstated trade-offs. Your new job is translating abstract engineering problems into structured constraints that an agent can actually reason against. You set the goal, you establish the boundaries, and the agent, it handles the syntax. Think about how we got here through the 3 distinct generations of terminal AI. First, we had basic accelerated autocomplete, synchronous line-by-line predictions. Pretty simple. Then came the second generation, chat collaborators living in your IDE panels. But the catch was they still required your active guidance for every single step. You were basically just an AI manager. Now we are fully entering the 3rd generation of autonomous harnesses, like Antigravity. These systems can ingest high-level requirements, formulate multi-phase plans, and run recursive tool invocations. That means they can independently use a tool, check the result, and then decide to use another tool based purely on that new data, all without stopping to ask you what to do next. Moving right along to Section 2, programmatic agent orchestration. Instead of relying on those manual chat interfaces, engineers are now using the google.antigravity SDK to initiate multi-agent runtimes entirely through code. You're setting up your clients, defining Pydantic schemas, and building out typed parameters to orchestrate automated workflows seamlessly in the background. You're completely done babysitting a chat window. You're building a resilient, automated machine. Now, comparing these cognitive topologies is absolutely crucial. Historically, agents used the react pattern. It's a single-thread, linear loop of reasoning and acting, and sure, it's fast, but its fatal flaw is that it's highly prone to unrecoverable cascading failures. One tiny mistake early on, and the whole loop just crashes. Instead, we are moving toward a hierarchical multi-agent model. Here, a central orchestrator rapidly spawns and supervises isolated subworkers in parallel. It gives you this clean separation of concerns and completely protects the main agent's context window from getting overloaded if a subtask throws an error. And to keep these agents from spiraling into infinite failure loops, this orchestration is forced into a very strict explore, plan, execute workflow. Before a single line of actual code is touched, the agent maps dependencies in the explore phase. Then, in the plan phase, it literally authors an implementation plan artifact. This is huge because it creates a verifiable proof of work trail that you can audit. Only after that precise plan is established does the agent move to phase 3, execute, for controlled code modifications. And we're talking about deep structural AST transforms, abstract syntax tree transforms, where the code rewrites itself, safely, based on strict structural rules, not just blindly finding and replacing text. All right, Section 3, structured data extraction. This is literally the ultimate challenge we face. We have to take unpredictable, inherently stochastic AI text, which, let's be real, is essentially randomized guesswork based on probability, and turn it into perfectly reliable, deterministic application data. Data your production pipelines can actually use. Because if the AI spits out a string when your pipeline explicitly expects an integer, everything breaks. I want you to visualize this process. Imagine a chaotic, unpredictable cloud of raw, model-generated text. It's unstructured, it's messy. Now imagine forcing that chaotic cloud through a rigid structural grid shaped exactly like a Pydantic class. What emerges on the other side? Clean, perfectly validated, strictly typed JSON objects. It's like magic, but it's just great engineering. This extraction process is an absolute non-negotiable for building stable systems. Thankfully, we have some incredible frameworks to pull this off. Libraries like Instructor, for instance, wrap Pydantic schemas and automatically handle retries if the AI messes up the validation. If you need absolute determinism, tools like Outlines mathematically guarantee the output at the token level using logic masking. Basically, it physically restricts the AI from generating invalid characters during the inference process itself. Crazy, right? And then there's BAM, offering a schema-first, domain-specific language for compile time safety, locking in your types before the code even runs. When you combine those techniques, you unlock programmatic tool calling. Instead of an agent dumping massive raw API logs directly into its context window, it writes a script to process it. By ensuring these tools execute programmatically inside a local Python sandbox, we only return refined, structured summaries back to the agent's main context window. This saves hundreds of thousands of tokens. It keeps the agent from forgetting its original instructions due to context overload, and it definitely keeps you from racking up insane API bills just because an agent decided to read a gigabyte log file. Which brings us to our final section, secure sandboxed execution. Because all of this begs a pretty big question. How do we actually let these agents execute local tools safely? Well, think of sandboxing as a secure, transparent containment shield. It enforces strict OS-level isolation. It allows the SDK to run bash scripts and build entire applications inside an impenetrable bubble, using tools like temporary directories or app containers. This completely shields your host machine. If an agent somehow decides to try and delete the root directory, it only happens inside the simulation. Your machine is safe. Inside that shield, the SDK basically gives you superpowers through programmatic interception hooks. You have inspect hooks for silent telemetry auditing that doesn't slow anything down. You've got decide hooks acting as blocking middleware, so if an agent attempts unauthorized file access, the policy just stops it dead. And transform hooks let you dynamically scrub out passwords or rewrite payloads before they ever hit the model, keeping your credentials completely locked down. And hey, if a subagent does go rogue in its sandbox and enters some wild hallucination loop, temporal workspaces and shadow Git branches act like a literal time machine. You can instantly revert the state back to a pre-prompt checkpoint without polluting your actual Git history. It's the ultimate peace of mind. So bringing it all together for the enterprise, this is your strategic blueprint for safely deploying orchestrated agents across an entire engineering team. You standardize the project context with declarative rules right out of the gate. You establish strict verification boundaries using CI/CD test hooks so bad code never even gets close to merging. You deploy the model context protocol to safely give agents access to your internal APIs. And super importantly, you configure maximum iteration caps to serve as hard circuit breakers against infinite loops. I'm going to leave you with this final thought. As we make this massive shift from just writing syntax to managing highly orchestrated, secure AI systems, how will you redefine your own engineering identity in this new paradigm? The tools are evolving faster than ever. It's time to start thinking like an architect. Thanks so much for joining me for this explainer, and keep exploring.